Hello, welcome back to another episode in CSC 263 in Database Management Systems at Adelphi University. In the previous videos we've looked at the SQL language and we figured out how to create very simple queries that can be used to insert data into a database and then retrieve it again, to more advanced queries that include nested queries, subqueries, aggregate functions, joins across multiple tables, etc. We've done all of these exercises on our command prompt in the database monitor, but that's not how we develop applications. The monitor is a great tool for figuring out what the query should look like, but of course that's not how you continue to use it in the real world. We usually typically build some form of a database application that does all of this for us. And that's the topic of this video. So as we do that, our system architecture changes of our programs. Specifically, until now, we have used on the top right our database, which we access through the database management system. But always to keep in mind that if we type PSQL on our command prompt, we're not actually connecting to the database management system directly. We're launching a utility application called the monitor. And the monitor is what connects to the database management system. So that is the part that we want to change to our programs rather than the program that is part of Postgres itself. And so when we look at the bottom where we see the first rounded rectangle which says database application, that's us. That is us developing software which uses database as a backend. The rest though stays the same. The database management system will accept our incoming connections, our queries, and will execute our queries against the database, and it will return the values to us in a format that we can use them. So as we start looking at how to do this from programming, this is what we are looking at. We are developing the database application. The database application is going to connect up to the DBMS, which interacts with the database directly. So regardless of what database management system you use, the recipe is more or less the same. The workflow is one, import whatever libraries you need to be able to connect to the database management system into your programming language. Then establish a connection to the DBMS. Then we establish what is called a cursor. That's not always done explicitly. It might happen under the hood, but it will happen. And the database cursor is really more of an abstraction that we use to execute queries and retrieve the results from the database as it has executed them. Like I said, in some libraries it's invisible, in other libraries it is explicit. Think of the cursor as the thing that keeps your place in the database, just like the cursor on the screen will keep your place on the screen. Once we have the cursor, we can create the query and then execute it. And in some cases those are two separate operations. In other cases they can be rolled up in the same utility function. Once we have created the query, and especially if it's a select query, we can execute it and retrieve the values that came back from the DBMS to our application. Not all queries return values. For example, an insert or an update operation, a create table or a drop table, they might not return anything other than success or failure with potentially an error message. Well, like I said, a select will return a list of values. The cursor takes care of all of that. All we have to do is talk to the cursor and it will tell us what we need to know. Since we have learned Python in our Introduction to Computer Programming class, this is probably the easiest language to demonstrate this in. And this is a fully functional program and it actually fits behind me on the slide. So step one was import our libraries. In our case, we're using the PostgreSQL database. There is a library called psychopg2, which we can easily pull into our programs, and that will take care of all the connectivity to the DBMS. Then we connect to the DBMS, which is the second line there, which says with psychopg2.connect. We have to give it at least the database name that we want to connect to. Each of us has our own database where your username is your database. But in more complex deployments where maybe the database runs on a remote system, you may have to provide additional information here, such as host names, port numbers, or whatever we need in order to identify where the database actually lives and which database we're looking for. That's going to give us a connection handle back. In our case, I called that the DBMS connection. With that DBMS connection, we can create our cursor, that's line 3. And then against that cursor, we can create a typical SQL query, the same way that we have been used to in the past. Notice that I'm using the triple double quotes here. That's Python's mechanism to specify strings that span multiple lines that keep the code nice and readable. And here we have the query that you should look very familiar to you at the moment. Now notice a couple of things. One, I'm not doing select star. I'm specifically naming what fields I want returned from the database. And that is because at this point, my program is fully separate from the database. The program can't tell the database what to retrieve, and the database, even though it can send data back, my program won't know what it means. Also, by specifying the columns here in the order in which I present them is the order in which the results will be returned to me. So my first result in each row will be the student ID. The last result in each row will be the posted field, which is the date on which the grade was posted. And each result should return into 6 fields, which I can then use to iterate over in step 6, where we're actually going to use them. And we can say for results in DBMS cursor, print result. And what you'll see is that you'll return for each of the rows in the result set a Postgres tuple, which is basically an immutable list of values that are indexed by position. And so we can try this and see what it runs like on our server. Now, this is an easy way of doing it, but there are a couple of disadvantages here. One, I'm embedding SQL directly into my program, and that means that any time that my database might change, I have to update my programs. Second, I am specifically calling psychopg2 here, and I'm using these psychopg2 specific functions throughout my code, which means that if I want to change what delivery mechanism I'm using or what database management system I'm using, I will also have to update all of my code, and that's not desirable. To address that, we have the ability to create an abstraction layer on top of that. So that is a layer that goes sit in between my program and the DBMS itself and does some translation from a generic format that I speak to a database specific format that it speaks on the other end. And the benefit, of course, like we said there, is that we now write our code that is independent of a specific database or a specific implementation. SQLAlchemy is one of those libraries that does that for us. It's not its own database management system. It is a layer that sits between us and the database management system. Now, first of all, when we look at this code, it looks like there's more going on here than in the first example I showed you. But that's a small price to pay. Let's forget about the imports for now. They just have to be there. So the first thing we do is create a new engine, which is very similar to connecting to the database, but except now it's a two-step process. The first step is defining what database management system we're using. In this case, it's Postgres using the psychopg2 library. And the second one, and the database that we are connecting to. The second one is then actually to make that connection. Now, at this point, this create engine line here is the only time when I do anything Postgres specific, which means that if I decide to switch my database to MariaDB or to SQLite or something else to that nature, I don't have to change a single line in the rest of my code. The only thing that I have to do is make a change here. If I decide to no longer host my database management system on a particular computer, I can update it here to point this engine somewhere else. Of course, ideally this goes in a configuration file or in an environment variable rather than be hard-coded in the source code altogether. But for clarity purposes, we'll leave it here for now. Then I'm actually going to tell my program what my database looks like. I'm going to tell it that I have a students table and that it has a number of columns. I'm also going to tell it which ones of those columns are part of the primary key, maybe if I have foreign keys where they are, and what data type I would expect to find in each of those columns. That's helpful because now the database and my program both understand the data that we're talking about. So that's a win. Now I can write more meaningful programs. And then lastly, on the bottom there where it says s equals select students dot where students dot c dot id equals 1, let's take that apart. Obviously the select statement here is mimicking the select keyword in SQL. Between square brackets is a list in Python, and what we're returning is students. That's the name of my table. If I don't specify it any further, I basically want to return all of the columns in students. That's okay now, because at this time my program knows what those columns are and what they are named and what the order is in which they appear. In the previous example, we didn't have that luxury, so we had to enumerate them one by one. Here, we have basically given that same information and more to my program, so now I can just say, give me everything. Dot where, that's my selection clause there. And in this case, students.c.id equals 1. Students is the name of the table. .c you can have as a shorthand for columns. So in the students table, I'm looking for the column .c with the name id.id, and the value of that column has to be 1. So realistically, what's happening is, select all from students where id equals 1. But I'm not writing the SQL itself. I'm writing an abstraction layer, an object-relational model abstraction layer on top of this, which is very similar to my programming language and doesn't worry about SQL at all. And then I execute my query and I iterate over the results. Arguably, this method is better because it is less dependent on the underlying technology. But you can give as a counter argument there, well, you just added an extra layer of complexity by importing additional libraries and putting them in between the database and the application that you are writing. Let's take another look, a little bit more detailed look at the previous example. So we're building on the previous example, which means that the students table is still defined, the connection to our database is already made. But we're now defining our second table called grades, and we're again defining all of the columns in grades, marking all of the columns that are part of the primary key as such, and give the appropriate data types. What I can do here is create these joined queries. Right below the grades definition, we'll see j equals join, and that's basically what I'm doing. I'm taking the students table and the grades table, and I'm joining them based on their common attribute, which for students is the ID column and for grades is the student ID column. So now I have a joined set of tables. Secondly, I'm going to extend my select query. Before I just said select students, I wanted all fields of the students table, but now I'm just saying no, from the students table I'm only interested in the last column and in the first column, and from the grades table I'm only interested in the grade column. So I can just eliminate what columns I'm interested in of the different fields that are part of my join. And I continue specifying my selection where students ID equals 1, and then I have to mention that I'm selecting this not just from the table directly, but from the joined statement that I have from above. And from that point on, I can continue using my program as normal. One of the benefits of using an object-relational model like this is that all of the Postgres-specific data types are translated automatically to Python-specific data types, and as a result I don't have to worry about to see if it fits. I have posted as a date. That means that in Python it becomes a datetime.date object. All of those things are very helpful. So this is how we take our knowledge of databases and use it to embed our SQL directly or indirectly, if we're using an abstraction layer, into a database application.